צהריים טובים לכולם, אנחנו ממשיכים, מוזמנים לתפוס את המקום שלכם בחזרה. אוקיי, צהריים טובים חברים, המשך יום נעים לנו, אנחנו ממשיכים. הדובר הבא שלנו הוא מר דייגו פדילה-פיליפס, אני אעבור לאנגלית ברשותכם כדי להציג אותו. Mr. Diego Padilla-Philipps, Net Zero and Lead and Structural Engineer, WSP. Decarbonizing is the challenge of our generation. And we only have one chance to do it, so we have to bring everyone to work together to achieve that. This is a quote from Diego's words. Diego is a net zero lead at WSP, and he will tell us about reducing embodied carbon in buildings. Please give a warm welcome to Mr. Diego Padilla-Philipps.
Shalom. Good afternoon, everyone. Thank you for the opportunity of being here. Thank you for listening in English. English is not my first language either, so thank you for the translator if I make any mistakes. And thank you for being here after lunch. I know it's difficult. Just after lunch, we all feel a bit sleepy, so hopefully you'll laugh at my jokes. Decarbonization is the most important thing we can do. It is a challenge of our generation, of the previous generation, of the next generation. It's something that we all need to focus on, and we all need to work together to achieve it, because we only have one chance to do it. That way. Sorry, thank you. Just 2 seconds about myself. I was born in Lima, Peru. I moved to the UK, to London, in 2009. I'm a structural engineer. But now I live in a city by the coast in England called Brighton. It's a small city, 300,000 people by the sea. I don't have a car. You walk everywhere. But I still work in London, so I get the train for an hour every morning. And it's interesting to see all these different contexts and how that shape who you are. And for the last 3 years, I've been working on supporting WSP's initiative to decarbonize our projects. The WSP is a global engineering firm. We have projects across the world, some of them here in Tel Aviv as well. I'm going to use one of them as an example later. Why is this important? Oh, yeah, sure, thank you. Okay. Thank you. I feel like it's Steve Jobs now. So it means I can talk now. The reason why it's important is because the built environment, all of our buildings, they generate 40% of the emissions globally. And I've seen this value already mentioned a few times this morning, which is great because it shows how everyone in this event is so connected and is so focused on the same objective. And it's so important. But it's more important in relation to what we can do as an individual. This is a building in the city of London. It's called 22 Bishopsgate. And I spent the last 5 years leading the design, the structural design for this building. It's an office building. And when we realized that the carbon emissions associated with this building, just the embodied carbon emissions, are around 100,000 tons. That is such a great amount. And as an individual in the UK, the average is 10 tons per year. So if I was able to save 1% of those carbon emissions, that is equivalent of 100 years of my life. So that is the power that each one in this room has. So if there's anything you take from this talk today is that 1% of your projects can make a massive difference. And someone mentioned earlier that Israel is a small market, but so is the UK. The UK generates 1% of the emissions globally. But it doesn't mean that we can't drive this change and this revolution. It means that we have this responsibility and this impact, so we have to make sure that we all work to achieve that. Oh, I think I turned it off. Thank you. And someone also mentioned this earlier, how important it is, because the effects are happening now. And coming from South America, where the carbon emissions per person are so much less than what we generate in Europe. However, we are suffering from those effects more disproportionately. That is why we have in this room so much responsibility in driving those emissions down. And it is happening. It's happening around us. That is Europe on fire. That is Pakistan underwater. That is Europe without any water. And that is Canada. So it is happening all around us, and we have just one chance to get this right. This is why we realized 3 years ago that the best that we could do as designers was to focus on the emissions from those designs that we create. And we made a commitment 3 years ago to reduce those by 50% by 2030. If you might be aware that the UK has a commitment to be a net zero economy by 2050, which means that by 2030 we need to be halfway there. So anything that we design, and this is structures, building services, facades, roads, bridges, we counted all of our designs in 2020, and then when we take the same measurement in 2030, it has to be 50%. It has to be half of that. And it's an absolute value regardless of growth. That is the power of what we can do as designers, as engineers, etc. Briefly, carbon emissions, 2 types of those, embodied and operational. For the last 10 years, there's been a strong focus on operational carbon, which is great. And green buildings and all of these certifications, they focus on reducing the emissions in operation. 50 or 60% of those emissions, as someone mentioned earlier today as well, come before the building is completed. It's the materials that we use, the embodied carbon. And those emissions are the emissions generating what we saw on the previous slide. Those are the emissions that we cannot see. They are in the atmosphere, and they are driving climate change. And those embodied carbon emissions are the ones that we need to focus. And structural engineers have a really massive opportunity to reduce them, because the majority are within the structure. So in the UK, there's been a few initiatives about reducing these emissions. So there was a benchmark carried out 2 years ago, and I'm just going to point at, is this the pointer? Yep. So, okay, thank you. So a typical office building would generate in the UK 1,000 kilograms of CO2 equivalent per square meter of construction. We need to reduce this. If we want to be a net zero economy by 2050, we need to reduce that to 350 by 2030. That is a 65% reduction in what we do. That is how big the scale, the challenge is. And that is what I'm going to show you today, how we're trying to do that. The first thing, of course, is measuring. So how can we... I've noticed earlier in the room that we're all focused on driving emissions down and reducing them. But how can we reduce if we don't know where to start? So the first thing that we can do is to measure them. So this is what we did 2 years ago when I led this study at WSP. We started measuring all of our projects. That way now we have a list of all of our buildings according to area, the bigger projects on the left and then to the right. And now we know, in relation to these horizontal lines, which is the standards and where we should be, we know where these projects are. And now we can help all of our engineers, when they do a design, to compare that against this and see where they are and what they need to do and what they can do to improve this. Now, one of these buildings is actually a building in Tel Aviv, I think. It's the one on the left. Yeah, it's the biggest one. But look at this. When you compare that, so in absolute terms, is the highest one. But if you divide that by the area, it is really efficiently designed. And this project I'll show you later is a collaboration between Ron Arad and Yashar Architects. And we did the concept design and schematic design, and then Israel David did the detail design.
But it was all focused on reducing those emissions at the beginning, from the early stages. Now, all this data now tells us how our projects are doing, what we can do to identify the challenges in those projects, and what we can do to reduce them. Now, the embarrassing thing is that that project that you see with the tallest one on the right, the worst performing building at WSP 2020, is one of the projects I led, which which is a massive eye-opener, and it shows you that we all have this responsibility. So we did this measuring, and I'm not going to bore you with the details of the values, but it's important to see that there's a massive distribution of all the projects. And some of them, as you can see in this on the left, some of them perform really, really well at the bottom of the scale in the green. Some of them perform really, really badly. But it's not until you see those values, until you understand these values, that you can really focus on reducing them. So I'm just going to skip through this quickly. So, how do we reduce carbon emissions? And this is an important subject, because what we need to change is everything. It's not just doing something a little bit better. It's changing the way we see the problem. It's changing the entire construction and design paradigm so that we can do things better. I attended a conference a few weeks ago, and someone said, if we knew now everything that we know about concrete and steel and how they're created, how they're fabricated, and we had an opportunity to create a new material, would we invent them again? And I'm sure the answer will be no. So now that we know, now that we have all this data, and now that we are gathering all this data in your projects, with all of that knowledge, would you do buildings in the same way? I think the answer will be no. So we first focus on changing the concept, changing the design philosophy. And the first thing that we're doing is reducing the amount that we build. The paradigm of design tells you that you need to focus first on doing less, which goes against all of our business models, because we always want to grow. But in this climate emergency, to prevent the climate catastrophe, we need to focus on doing less. And one of the obvious things is reusing existing buildings. We are working in the UK, and we're lucky to have a lot of existing buildings that we can reuse. And our clients are seeing that value because, as someone mentioned earlier today, the market is changing. Big tech firms have strong ESG commitments. They are looking at net zero certifications, which don't exist yet, but they're looking at them. They're looking at ways of offsetting the carbon emissions. I know for a fact that we had a project in the UK, very iconic project, and they couldn't let the top 5 floors because the clients were asking for something that they couldn't provide. So they had to change all of the mechanical services to comply with some net zero certification because they couldn't really sell those offices. And it's not about a green premium anymore. They used to say, well, is this more expensive? It's not about something being more expensive anymore. It's about not being able to sell that product that we are creating because the market is changing their perception. So instead of calling it a green premium, we now call it a brown discount. If your asset doesn't meet those certifications, you will not be able to sell it, which is a massive challenge. So changing this conceptual paradigm, changing the way we approach buildings, changing the materials we specify, because, of course, after you optimize materials as much as you can, then you have this big elephant in the room. You still need to, what do you do with concrete? What do you do with steel? So there's 2 initiatives that we signed up to. One is called Concrete Zero, and one is called Steel Zero. And in both, we have signed up to specifying 100% net zero concrete or net zero steel by 2050. What is this? We don't know yet because it doesn't exist. But we have committed to increasingly specify better materials in our specifications so that the market sees that there's more demand for these materials, and then technology catches up, and then the producers catch up, and then they start generating materials with less carbon emissions because there is a market for it. And this is the paradigm of design. This is the hierarchy of design that we all need to focus on. The first thing is build less. How can I use less? How can I use better materials in a better way? How can I use less of what I already have? The next one is build light. challenge those loads. In the structural engineering world, I don't know how many structural engineers are here, we add so much redundancy and buffers and extra loads because we think the client might change their mind later, and then the client says, well, we change our minds because there is capacity because the structural engineer has added this, and it's a vicious circle. And we keep adding these safety factors and things one on top of the other. And we keep doing things in a way that it's been done for the last 20 or 30 years, but that doesn't mean that it's the right or the best way to do it. So challenging those to use less materials, to build light, and then build wise. So once you reduce that, then how can I do things in a more clever way to use less materials, shorten spans, think about adaptability. For example, if I want to adapt this space so that in 20 years it can be used differently, instead of designing that with an extra load, just in case, because it might not happen, we can design it in a way that it can be strengthened if it needs to. And that way we save those carbon emissions now. And finally, we go into this one, which could be where the expense is, specifying lower carbon materials, because some of them are more expensive, naturally. But once you've addressed the first, what you save in materials, and you'll see from the example later, it's so much more than what any increase that you could create because of specifying some fancy type of concrete. Finally, build for the future, and of course, build collaboratively, because so many things require careful coordination between all the disciplines from the earliest possible stages. And I've got 5 minutes now. So what is the future of reducing carbon emissions? Or is it the present? So this is a tool that we already use at an early stage concept design. This is before the building goes to get planning approval. And you can test, this is a 80-story building in the City of London. You can test hundreds of options at the early stage to see the interaction between embodied carbon, operational carbon, and daylight factors. Because if you think about these three factors, they all compete against each other. If I want a building to be the most efficient in terms of facade, it will have a specific orientation. It will be quite skinny in the north-south to avoid the solar gains, etc. It will be quite slender. If I want to optimize this from a embodied carbon perspective, it will be compact and low, because the taller you go, the higher embodied carbon emissions. And if I want to optimize it from an operational side, it will be compact, it will be sometimes a basement because you want to use, that insulation from the ground. So the three options compete against each other. So what if we had a tool that can test at the same time so many alternatives and then try to find this most optimal solution for all of them? And what if we could do this at the early stages when cost decisions are made, before even the architect is involved? Supporting the architect with the site parameters and then shaping that building so that it meets all the requirements from all the stakeholders. So that is what we're doing now. We're applying this for projects, and this is how we can all change those design paradigms from the early stages and generate hundreds of options at the super early stage, and then see what is the most efficient way of using those materials and saving money for our clients. And we can test those and see and try and find the most efficient way. And what this does is it generates hundreds and thousands of models so that then we can train a computer through machine learning so that in the future they can just predict these values. But is this the future? I think it's the present. Now, what did we do in this fantastic building that I've got behind me? This is one of the most beautiful buildings I've worked on. It's this collaboration between Ron Arad and Yasha Architects. Is Toha 2 here in Tel Aviv. It's currently the basement's being built, but Toha 1 right next to it is already completed. The geometry was incredibly challenging, but the geometry lended itself to parametric studies and optioneering so that we could reduce the materials with the support of computational tools. So what did we do in this project? The first thing that we did was, let's find the most efficient, multidisciplinary core, because in a tall building, the stability system drives. And especially in an area like Tel Aviv, with moderate to high seismicity, but also high winds. Now, this one drawing is the result of months of coordination between the vertical transportation engineers, the structural engineers, the mechanical engineers, the architects, to find the most efficient shape to respond to this challenge. And once you have that, you put it in a computer and you do a wind tunnel test, and then you find the ways to reduce those thicknesses, to use the least amount of materials possible, and to use those in the most efficient way. I know I keep saying the word efficient, but there's a reason for it. It's because when we did that assessment in the UK 3 years ago, the reduction had to go from 1,000 to 350. But the first 25% of the savings are in inefficient design. Inefficient design that we all do, that we structural engineers add extra safety factors, add extra loads, the mechanical engineers add this extra stuff, and everyone adds things or everyone does things in the same way, and we carry on using systems inefficiently. So if we all focused on reducing those, we could save straight away 25%. That is what we say, it's the low-hanging fruit, you know, the easy win. Let's design efficiently. So for Doha, what we did was every single column is different. Every column had a different inclination and therefore attracted different forces. And there was this careful coordination with the architect between the inclination, the facade, the structure, the services. So we optimized this so that through this computational strategy, you could identify how many different inclinations you had and different column diameters, because then that is translated into construction benefits. Because if you only have a few inclinations, you can build things faster and in a cheaper way as well. So we went from 90 individual column types to only 25. At every stage of design, we improved this to make it even better. And this was not just computationally automated. In the end, it also had an element of manual design, you know, with getting with the architect and thinking, what if I move this by this much, by 20 centimeters, and how that impacts and how we can optimize that. This is a view of the building from the top. As you can see, it's very difficult to picture, but imagine you're flying above the building and you can see all the columns on the left-hand side. The first thing you do is you make them planar. You align them so that you can make it easier to build. And then you start from 90-something different inclinations and angles, and then you group them, and then you find the repetitions and find the most straightforward way of delivering this. We did the same with the concrete strength. We divided the building in different sections, and then we ran an analysis to see what was the most efficient way of increasing the concrete strength so we could reduce the column size, so we could reduce the weight of the building, reduce the foundations, increase the area, the lettable area. And we found what was the most optimal cycle for this. We compared, what if we change the column diameters every 20 floors, like you can see on the right, or every 10 floors? How many unique column diameters and heights do we get, and inclinations do we get? Because each diameter is a different type of casing, etc. Then we took that to the design, and then we also analyzed the horizontal forces created within the building. All of this parametrically and in an automated way. But the most important thing was the slab sizes. So we tried 5 different types of slabs, and then we found that every floor was of a different size. So the distances between the core and the columns were different. So we assessed every single one, and every time we moved the column, it changed this. And then we could find, how do we optimize these elements? How do we move away from a single slab thickness to reducing the slabs according to distance so that we could save 11% of the materials? So this is what we achieved just by efficiency in the geometry. By reviewing the wind loads, we saved 2% of concrete tonnage. That's 2% of the cost of concrete. By using the wind tunnel, another 5%. By optimizing geometry, another 2%. And the slab thickness is another 4%. So 13% savings just by building a little bit lighter, building less. If we had introduced further optimizations, we could have added an extra 4% by using outriggers and the stability system, and an extra 10% if we could have reduced the spans even more. And then finally, if we had used the less cement in the concrete mix, we could have reduced an extra 50%. So a project, a tall building like Doha, could be done using 37% of the materials and the carbon emissions that you normally do currently in Israel. And it can be done, and it should be done. So my final thoughts are, I love these numbers, 2050, 2080, and 80-20. 2050, that's when we need to be net zero for. Some people say it's too late, it should be 2040. 20 and 80, they say that 80% of the projects, of the buildings that will be occupied in Europe by 2050 are already built, 80%. So we need to reuse them. However, in the rest of the world, in South America, where I'm from, in Africa, in Asia, in India, it's the other way around. 80% of the buildings need to be built. And therefore, that is why reducing those emissions, upfront carbon emissions, is so important, because we build the equivalent of a city the size of Paris per week, or a city the size of New York every month. So what are you doing about it? Thank you.